Okay, so as an enterprise architect, you know that data is pretty much your most valuable asset, right? But what if the very structure of your database is hiding your most important insights? What if the key to unlocking all this new value isn't just in the data itself, but in the connections between the data? Today, we're going to dive into the world of graph databases and see how they can completely change the game. You've probably felt this pain before. Your system starts slowing down to a crawl, and it's because you're asking what should be simple questions about connections. You know, things like finding friends of friends or tracing a part through a complex supply chain. And your trusty relational database, which has been the workhorse for decades, is just struggling to keep up. Let's dig into why that is. So the problem is that dreaded join operation. In a relational database, finding connections means you have to link tables together. It's kind of like a chain of phone calls. With every new link you add, the query gets way more complex, and the time it takes just grows exponentially. Performance completely grinds to a halt. A graph database, though, approaches this in a totally different way. It does what's called a traversal, which is more like following a direct pre-existing path from one point to the next. And that means it keeps its speed no matter how deep the connection is. To really solve this, we have to shift our thinking. Instead of calculating relationships on the fly with those super expensive joins, we need a system where the connections are stored directly. They're treated as first-class citizens, just as important as the data points themselves. And that, right there, is the core idea behind a graph database. Now, here is the secret sauce that makes it all possible. It's called index-free adjacency. Think about it like this. Every single piece of data in your database has its own little address book. And that address book contains direct pointers to everything it's connected to. So when you want to find its neighbors, the database doesn't have to search some massive global index. It just looks at that local address book. This makes finding connections almost instantaneous. It's a total game changer. So how do we actually build a system like this? Well, it all starts with a simple but really powerful set of building blocks. It's called the property graph model. Let's break it down. First up, we have nodes. These are our entities, the things we care about, like a player or a team. Then we've got relationships, which are the directed, meaningful connections between nodes, like a player who plays for a team. Now, what's cool is that both nodes and relationships can hold properties, which are just key value pairs of data, like a player's salary. And finally, we use labels to categorize our nodes, like tagging someone as a person. Simple, right? Okay. Theory is great, but let's put this into practice. We're going to model a really simple relationship just to see how intuitive this all is. We'll take a player who plays for a team. So we start by creating our two nodes, one for our player, let's call him John Doe, and another for the All-Stars team. Simple enough? Next, we draw a directed relationship between them, showing that the player plays for the team. But here's a really key feature. We can add properties directly to the relationship itself, like the contract year. This is awesome because it describes the connection, not just the things being connected. All right, so now we have a blueprint for our data. But how do we actually talk to this new database? Well, we use a query language designed specifically for graphs, and it's one that actually looks a lot like the patterns we're searching for. Let's take a quick look at Cypher. What's so cool about Cypher is its syntax. A lot of people call it ASCII art because you use parentheses for nodes and square brackets with arrows for relationships. This means your query literally looks like the diagram you draw on a whiteboard. It makes writing and reading queries so much more intuitive. A basic query is really just a simple three-step process. First, you match the pattern you want to find, in this case, a player who plays for a team. Then, you use where to filter that pattern, saying we only want the team named All-Stars. And finally, you use return to say exactly what information you want to get back, like the player's name and their salary. That's it. Okay, this is super important. When you're adding data, choosing the right command is critical. If you use create to add a player who's already in the database, you're going to end up with a duplicate, and that can really mess up your data. The best practice almost always is to use merge. Merge first tries to match the pattern. If it finds it, great, it does nothing. If it doesn't find it, only then does it create it. This is how you prevent duplicates and keep your data clean. So as we're planning our implementation, these are basically the non-negotiables for building a solid high-performance system. Rule 1, always use merge. Rule 2, when you're loading a ton of data, use unwind to process it in efficient batches. Rule 3, create indexes on key properties, just like you would in a relational database, to speed up those initial lookups. And finally, remember to store data on relationships when it really describes that connection. All right, let's move up to the application layer and see how this all plugs into our existing enterprise services. And we'll focus specifically on Python. So the first step is just establishing that connection. With the official drivers, like the one for Neo4j, it's honestly just a few lines of code. You import the library, you create a driver instance with your database address and credentials, and boom, you're ready to start sending queries from your application. It's that easy. And here's a huge pro tip for both security and performance that you absolutely cannot skip. Just like in the SQL world, never ever use string formatting to inject variables into your queries. Always use parameterized queries. This protects you from what's called Cypher injection attacks, and it also lets the database cache the query execution plan, which gives you a major performance boost for queries you run often. Okay, now we get to the final and maybe the most critical step in our journey as an architect, picking the right tool for the job from this growing ecosystem of graph database platforms. The landscape out there is pretty diverse, and each platform is really optimized for a specific kind of job. You've got Neo4j, which is the market leader, great for general purpose stuff. For teams that live and breathe AWS, Neptune offers a fully managed service. If you're doing really deep, complex analytics across billions of connections, TigerGraph is built for that kind of scale. For real-time streaming, Memgraph's in-memory speed is its killer feature. And for all the new Gen AI and GraphRAG stuff, FalkorDB actually offers native vector search right inside Cypher. So ultimately, my decision as an architect really comes down to this core trade-off. Do we go for operational simplicity with a managed cloud service like AWS Neptune? I mean, that gives us zero admin overhead, which is amazing, but it can be slower and the I/O costs can be unpredictable. Or do we opt for a self-managed solution like Neo4j? That gives us maximum peak performance and full control, but it requires serious operational know-how to manage the cluster. So the key is to map this all back to our primary use case. If our queries are mostly transactional, short, fast lookups, Neo4j's architecture is perfectly optimized for that. If we're doing these really deep analytical queries that go 5 or more hops deep, a platform like TigerGraph is designed to crush that. And if our number one priority is just ease of management and we're okay with the performance trade-off, then a managed service like Neptune is the answer. The big takeaway from all of this is pretty clear. If the connections are the data, if the relationships themselves are what drive your application's functionality, then you really need a database that was built from the ground up just for those connections. And that leaves us with one final thought to chew on. We figured out how to solve today's problem of querying connected data efficiently. But as all our data sources get richer and more interconnected, from IoT to knowledge graphs, this shift in perspective, from thinking in tables to thinking in networks, well, that might just be the blueprint for the future of all enterprise data architecture.